Good morning. Happy Wednesday. My name is Kayla. I'll be your Toastmaster for today. Today we're going to have a lot of fun. We have a couple of group leaders lined up to present about our experiments next week, and then after that we're going to finish up with some table topics. So first up, I'm going to have Morgan come up and talk about the bomb calorimeter experiment. Is there a pointer anywhere? Oh. No, I can just, you can just let me do it.
Okay. I'll bring it next time.
Okay.
All right, guys. Once again, I'm Morgan Bollinger, or my middle name is Burke, so I just go by Burke. We're going to talk about the bomb calorimeter. Go ahead and click on to the next slide. So, when I was starting this PowerPoint, I was trying to think, okay, how can I engage the audience and kind of give them a background before we kind of dive a little bit deeper into actually what a bomb calorimeter is. So I thought of, okay, well, I think one of the very basic questions we have is what is enthalpy? And so I kind of wanted to set this up as somewhat of an interactive presentation. I don't know if that's okay, if we do more interactive. Okay, well, let's go ahead and kind of do that then, because I just thought maybe that might be kind of cheating some time. But anyway, so anybody have any idea what enthalpy is? Yeah, sure.
The textbook definition, because I had to look at it as well, is like the sum of the total energy of the system and the product of the pressure and the volume of the system.
That is absolutely correct. That's perfect. Yeah, so like Trip said, enthalpy is basically the internal energy and the energy it takes to disperse the surroundings, which, as Trip mentioned, was the pressure times the volume. All right, so go to the next little click. So my next question is, what is the change in enthalpy? And it should be kind of pretty obvious what it is, so you go and click it. Well, of course, the change in enthalpy is the change in internal energy and the change in the energy it takes to disperse the surroundings. But the corollary to that question is, what if there's a constant volume? And this is important because this goes back to what a bomb calorimeter is, which we'll talk about in a bit. So does anybody have any idea what happens if there's constant volume? No? Okay. Well, basically what happens is that pressure times volume goes away because volume is constant. And so what you'll get is that you'll get the change in enthalpy is basically heat. And what happens is that when the bomb calorimeter goes off, we'll talk about this a little bit in a little bit. But what happens is that the heat is absorbed by the water, and we'll see that, when there is a spark that ignites a sample. So you go ahead and click. Yeah, so in this experiment, we'll operate in a constant volume environment, and this allows us to measure the heat released by the reaction using some type of thermocouple or thermometer. So you can go to the next slide. All right, so this is an oxygen bomb calorimeter. I made up like a really crude, like paint type drawing. So anyway, these are the main parts of the bomb calorimeter. You have the bomb, which is some type of really like very robust stainless steel, basically like container that's filled up with oxygen. You have wires coming down from an apparatus. They ignite a spark, or they make a spark which ignites a sample in a very oxygenated environment, which is under a constant volume. There's water surrounding the bomb. There's a stir that allows the water to kind of stir around in the entire apparatus. And then there's a thermometer, in our case it's a thermocouple, that measures the temperature. So go to the next slide real quick. Yeah, so what happens is the spark will go ahead and ignite the sample, and the heat, which is represented by the arrows, is released into the water, and the thermometer takes the temperature and takes the change when we ignite the benzoic acid in this case. So you can go to the next slide. So these are the goals of our experiment. We want to familiar ourselves with the physical properties, the proper procedures, and the techniques of an oxygen bomb calorimeter, and we're to determine the thermal capacitance of the bomb calorimeter and the gross heat of combustion of the samples that were given. In this case, it's benzoic acid, and you can go to the next slide. So here we are, we have what is thermal capacitance. Thermal capacitance is this mass times specific heat. In our case, it's constant volume environment, so that's why we have the V there for specific heat, where mass is M, C is specific heat, Q is the heat of combustion, and of course delta T is change in temperature. And then furthermore, what is the gross heat of combustion, which is Q, and it's kind of the same idea here. Go to the next slide. Okay, so here's some predicted results. Of course, I'm human, so I made a mistake, so you can check that. But I just kind of go through here and I just say, okay, thermocapacitance is mass times the specific heat. We're given roughly 2 kilograms of water, 3 kilograms of stainless steel. I assumed it to be 3 or 4. I'm not sure what it was, so I just assumed 3 or 4. And then I just went ahead and I solved. I found that the specific heat, I just looked up on the internet, it's 4.18. Specific heat of the stainless steel is half kilojoules per kilogram Kelvin. And I found out the thermocapacitance of water, thermocapacitance of stainless steel, and I took those numbers and I said, okay, well, it has to be between those two, so it's probably about roughly 5 kilojoules per kilogram, per Kelvin. So then they asked us to predict what the temperature rise was for benzoic acid out of a 1 gram sample. So I had to find the molar mass, and then I had to find a few other numbers, and I came out with the change in temperature would be about 5 Kelvin. Now personally, I feel like that's probably a little bit too high, so I would expect it to be less than that, but we'll check. I don't think anything, I think something's a little higher than that. I think it's probably off, but we'll see. So we go to the next slide. So also what was asked of us was to talk about some uncertainty or some errors that we might have in the experiment. So I kind of listed out a few things. They explicitly asked us to not have more than 1.1 grams of fuel in the bomb calorimeter because having too much of the fuel, I guess, could really create a bomb. That's my understanding. So it's probably not a good idea to have that. Also, the chamber has to be pressurized. The bomb itself has to be pressurized properly. For instance, one of the things they talked about was having some of the O-rings could be improperly sealed, so we're going to just check to make sure that everything's sealed up properly. There could be an improper amount of water inside of the actual container itself around the bomb calorimeter, so we want to make sure that that's proper. They also talk about that the tolerance of the water itself needs to be plus or minus 5 degrees of the room temperature. And so I think that, I wasn't really sure, they never really explained that too much, but I just want to say it's probably because we don't want there to be wild fluctuations between the water itself and the room temperature. So we're measuring the change in temperature. Well, we don't want the water to be incredibly cold and it keep on rising anyway because the room temperature is way hotter, or vice versa. There could be improper data logging. When you go to the computer, you might click on the wrong thing, so we should make sure that everything we're doing is correct. Also, there could be some improper stirring of the water itself. Is that 6 minutes? We're good? Okay, so real quick, this is the last slide before questions. Why is bomb calorimetry important to us? There are certain heating values of fuel. So when we think about what is a really poor fuel, for instance, firewood would be a pretty poor fuel, although it's necessary. But a really good fuel might be enriched uranium. So when we're talking about higher and lower values, it's important to know that maybe for us as a society, some type of nuclear reactor may be way better if we had those than, say, a firewood burning plant, for instance. Also, one of the things that we need to look out for is the enthalpy of vaporization, which is what it takes, or the amount of heat it takes to vaporize a substance. And with that, I think the next slide is going to be questions, and I'll open up the questions.
On that last slide, was that just the amount of heat it gives off per mass of material? Is that what that means?
Yeah, well, yeah, it's the energy per kilogram, yeah, per mass, per unit mass. Yeah?
You mentioned improper stirring. What does that mean?
Okay, so go to, I think it's this third slide maybe. The example, yeah, there it is. So there's a stir in here that stirs the water. My understanding is we want to have a constant environment where, say for instance, you don't want let's say it's really cold down here and then really hot up here. You want it to be kind of like an average. So you want to have the water stirred and mixed up a little bit. That's my understanding of it. And I don't know if maybe we could go more into detail of that, but when I watch videos, that's what they explain it to be.
Thank you.
Yeah.
Those two cables, are those positive and negative wires going in?
Yeah, I just represented that as wires, yeah.
Okay.
It's just a pictorial representation. It might not be 100% correct, but yeah, the wires just come in, they have an electrical charge and spark, boom, and then you ignite the sample in an oxygenated environment, and it lets off heat. Yeah.
Are all the samples combustible, so like you wouldn't use a wood in this?
I think in our case they asked about benzoic acid, but I would think that you could do pretty much anything. In fact, one of the videos I watched is sometimes there's endothermic, there's exothermic reactions. So sometimes maybe it'll get colder, but I haven't seen that. Most of the things I saw were like they take like hydrochloric acid and like a sodium hydroxide as like a base, and they mix them together and then have like exothermic reaction. But in some cases, I'd imagine if you set it up in a proper way that it can be colder, and I think you can pretty much put anything you want in there as long as it's small enough. All right, sounds good. Thank you guys.
Thank you so much.